Okay, chapter 21 is on musical sounds. We'll talk about pitch, intensity and loudness, and quality of sounds. So noise is sort of an irregular vibration of the eardrum that's produced by vibrations that have a jumble of amplitudes, frequencies, phases, and all mixed together. So white noise would be an even mixture of all these frequencies. It sort of sounds like shh, and if you plot pressure versus time, you just get this big jumble with no particular frequencies standing out. Music is the art of sound, and musical sounds have a rather periodic and pleasant-looking plot of pressure versus time. And a musical tone has three characteristics: pitch, intensity, and quality. Pitch is related to the frequency of the sound waves, and it's determined actually by the fundamental frequency, the lowest frequency you hear. Intensity determines the loudness of the sound, or like the amplitude. And quality is determined by the presence of harmonics, or different frequencies all combining to produce the same sound. And these are called partials. And so the relative intensity of all the various partials gives us the quality of the tone. So let's start with pitch. Music is organized into notes. Each note has its own pitch, which we can describe with a frequency. The rapid vibrations, or high frequency, produce sounds with a high pitch, and slow vibrations, low frequency, produce sounds with a low pitch. So in music there's 12 distinct notes. We start with C, then there's, if you go up by semitones, there's C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, and lastly B. And if you go a semitone above B, you're back to a C. Each semitone represents a multiplicative step of the 12th root of 2 from the note before it in frequency. And that's about 1.059. And if you multiply 1.059 times itself 12 times, you get 2. And so 2 is the step in frequency from one octave to the next. So this C down here has a frequency of 32.7 hertz. The next C up has a frequency of 65.41 hertz, etc., etc. So different musical notes are obtained by changing the frequency of the vibrating source. High frequency produces a high pitch. Lower frequency, maybe a larger musical instrument, for example, or a more massive one, will vibrate with a lower frequency, and you'll get a lower pitch. And in music, the pitches we use up at the very, very high end, like a piccolo, go up to about 4,000 hertz. That's about as high as you want to hear during music. But in fact, your ear is sensitive up to maybe around 18,000 hertz. Certainly, even some people and most dogs can hear even a little above that. But this upper limit, as we said before, kind of goes down as you get older, meaning that a very, very high-pitched sound above 18,000 hertz might be inaudible to someone like me, but a younger person might be able to clearly hear it. So there was pitch. Next one is intensity. Intensity of sound depends on the amplitude of the pressure variations. So high amplitude is loud, low amplitude is like a whisper. So the human ear responds to intensities from the tiniest little whisper of 10 to the minus 12 watts per square meter. That's called the threshold of hearing. And all the way up to the threshold of pain, which is 1 watts per square meter. That's 10 to the power 12, which is like a trillion times more intense in terms of power going into your ear. Separates the tiniest whisper from the threshold of pain. So because of this big range, the sound scale we use for sound intensity is a logarithmic scale, meaning that as you go up each additive step of 10 decibels, you're actually multiplying times a factor of 10 the actual intensity in watts per meter squared. So we define the threshold of hearing, 10 to the minus 12 watts per meter squared, to be 0 decibels. 10 decibels is 10 times more sound intensity than the threshold of hearing. 20 decibels is 100 times the sound intensity of the threshold of hearing. 30 decibels would be 1,000 times, all the way up to this threshold of pain. It's 120, so it's actually 1 trillion times more intense. This is an air raid siren nearby, and this jet plane 30 meters away is actually 140 decibels. That's above the threshold of pain and can actually damage your eardrums. The sound intensity you can actually measure in watts per meter squared. It's the amount of power per cross-sectional area. But loudness is a physiological sensation. So it turns out that our ear is most sensitive to about 3,500 hertz. It's a very high-pitched note. So a 3,500 hertz sound at 80 decibels sounds twice as loud as 125 hertz sound also at 80 decibels. Okay, so we did pitch, we did intensity. The last one is quality. So we know that if you play the same note on a piano or a clarinet, you can hear the difference. That's called quality or timbre. Timbre describes all the aspects of the musical sound that are other than just pitch or the loudness or the length of the tone. So one way of describing the timbre is to note that a particular tone is often composed of a fundamental frequency and then higher frequencies that are multiples of that fundamental frequency. So this is related back to standing waves, where you can have first harmonic, second harmonic, third harmonic are all integer multiples of frequency. Well, any tone played on a real musical instrument is actually a sum of the lowest harmonic plus a lot of these upper harmonics. So for example, you might get a string that's vibrating both in the fundamental mode and in the third harmonic together, and that will produce a certain timbre of sound. So all these partials, okay, the presence of the partials and the relative intensities of the partials determine the quality of the sound. And so the reason a piano and a clarinet sound different is because they have either different partials or different relative intensities of these partials. And when you add them all up, you get these different shaped wavefronts, or different shaped pressure versus time graphs for piano and a clarinet. So Fourier analysis is the mathematical analysis of these different partials. So Fourier discovered that any wave can be dissembled into a sum of just sine waves. Okay? And so if you have a composite wave, this one down in the bottom, it can be the sum of the fundamental sine wave plus the second and plus the third harmonic. You just adjust the relative amplitudes of these harmonics, and you can make it sum up to look just like this composite wave. So any musical note is actually the sum of a bunch of different sine waves of different frequencies. And that's what we hear. That's how we can hear with our ear and tell different timbres of sound. So an audio recording is simply a way of recording somehow the pressure versus time of a sound. Okay? This is actually the sound of an oboe and a clarinet being played together. Okay? It's some complicated waveform, but a phonograph record actually can record an analog signal which is of this shape, so that when you play it back, that's how it moves the speaker, and that's what we end up hearing. So digital sound is when you take this plot of pressure versus time and turn it into numbers. Each number describes the amplitude at a particular instant of time. And we can record that, all those many, many, many numbers, on the surface of a DVD or a CD. And so this is a microscopic image showing pits, where each little short pit corresponds to a 0, a long pit corresponds to a 1, and many, many of these pits form binary numbers, and each binary number tells you the amplitude of the sound. And then when it gets played back, all that amplitude tells the speaker how to move and how to create that pressure versus time wave, and that's how we hear exactly the music that was originally recorded. Okay, chapter 22 is on electricity and electrostatics. So we start with a new force called the electric force. So if any two objects have electric charge, there's a force between them. And if the two charges are alike, then the objects will repel one another, like plus plus or minus minus. If the charges are opposite, then they'll attract one another, like minus plus or plus minus. So we have to go back a little bit and review what atoms are made of. Remember, atoms are made of protons, electrons, and neutrons, where protons are positive. So that's their electric charge, meaning that they repel other positives but attract other negatives. And electrons are negatively charged. So they repel other negatives but they attract positive charges. And neutrons have no electric charge, we call them neutral. Some fundamental facts about atoms. 1, every atom is composed of a positively charged nucleus surrounded by some negatively charged electrons. And every electron is identical to every other electron in the universe. Every proton is identical to every other proton in the universe. And every neutron is identical to every other neutron in the universe. So there's really only 3 kinds of particles. Thirdly, protons and neutrons compose the nucleus, and protons are about 1,800 times more massive than electrons, and yet they carry the exact same charge, but just the opposite sign. And neutrons are about a little bit more massive than a proton, but they don't have any charge. And since protons and electrons have equal but opposite charges, a neutral atom is one that has the same number of electrons as protons. So here's a lithium atom with 3 protons in the nucleus and 3 orbiting electrons, so it has net charge 0. If an atom does not have the same number of electrons as protons, we call it an ion. A positive ion has lost 1 or more of its electrons, and a negative ion has gained 1 or more extra electrons. So in an atom, the innermost electrons are attracted very strongly to this oppositely charged nucleus, but the outer electrons sometimes can get dislodged. For example, this girl sliding down the slide, electrons may be transferred to the plastic. It can also happen with a comb. Okay? So the comb or the slide here ends up negatively charged, and your hair ends up with a positive charge. It can also happen when you rub a piece of glass with silk. But in all cases, there's conservation of charge. So if you have this rod that gets negatively charged, that means that whatever you rub it with will have positive charge. You can't create or destroy electrons or protons. You just move them around. So here we have 2 particles, and they have charges Q1 and Q2, and they're separated by some distance d. So if these charges are alike in sign, there will be a repulsive force between them. If they're opposite in sign, there'll be an attractive force between them. And the size of this force is given by Coulomb's law. So here it is. F equals K times Q1 times Q2 divided by d squared, where K is Coulomb's constant. 9 billion newtons times meters squared per Coulomb squared, where Coulomb is the SI unit of charge, and d is, like I said again, the distance between them in meters. So this looks similar to Newton's law of gravitation, and this force actually underlies what bonds together atoms to form molecules. But the difference between this and gravity is that this force can be repulsive or attractive depending on the signs, but gravity is always an attractive force. So a conductor is any material where the electrons are free to move around within the material. They're not really attracted to their individual nuclei, like copper or aluminum, for example, metals. And insulators are where each electron is tightly bound to its particular nucleus. So rubber or glass has this property that it doesn't want to conduct electricity. So here's a rubber mat, and you can stand on this rubber mat when you're doing electrical work to keep you safe. Charging by induction. So if you have a charged object and you bring it near to another object, you can electrify that other object without even touching it. For example, sometimes a thundercloud will shift charge around it so the top surface is positive and the bottom surface is negative. What that can do is that these negative electrons in the thundercloud can push away electrons in the top surfaces of these houses and trees, basically pulling a positive charge to the top of these buildings. Charge polarization. So an atom can be polarized. And what that means is, for example, here's atom A. It has an electron or some electrons that are orbiting around a nucleus. And the center of this cloud of electrons is centered right on the positive nucleus. But if there's some external charge, like an external negative charge brought to the right of this atom, then what will happen is that that'll push the electron cloud to the left and pull the nucleus to the right, separating these two objects. So this is called a polarized atom, where more of the negative charge is to the left, more of the positive charge is to the right. And this can happen in bulk for many, many atoms in a solid. So here's a negative rod brought towards this wall. Well, all the atoms in this wall end up being polarized, with their positive part pulled to the left and their negative part pushed to the right. And what this can do is it can create an attractive force. So, for example, here's a positively charged comb brought next to a tiny piece of paper. Well, that positive charge can polarize the paper. It can pull the negative charges to the side that's closer to the comb and push the positive charges to the side that's further away. But if you look at Coulomb's law, it says that closeness creates a bigger force. Right? This is the inverse square law. So this attractive force towards the comb is bigger than the repulsive force, and the net force on the piece of paper always ends up being attractive. And this is why if you rub a balloon against your head, it always is attracted to a wall, because the balloon picks up some charge and then it polarizes the wall. So if the balloon is negative, it pulls positive charges in the wall towards the balloon, negative charges away. Again, closeness wins, so the net force of the wall is pulling it towards the balloon. And by Newton's third law, the balloon is pulled towards the wall. So when there's an electric charge, we say that the space around the electric charge has an electric field, which describes the electric force. And the electric field obeys the inverse square law according to Coulomb's law. So electric field is the force per unit charge. It has the same direction as the force would be on a positive charge, opposite direction that the force would be on an electron. So electric potential energy is energy possessed by a charged particle due to its location in an electric field. So for example, for a gravitational field, we have this object hanging from a string. You cut the string, then the object will move, changing its gravitational potential energy into kinetic. If you have a positive charge tied to a string near a negative charge and you cut the string, the positive charge will also move. And so we say then that's converting electric potential energy to kinetic energy. So that's for an attractive force. For a repulsive force, you might want to think about a spring. If you compress a spring by doing work on it, you are adding energy to the potential energy of the spring. If you take a positive charge and push it towards another positive charge, you're adding electric potential energy to this electric field. Electric potential is the electric potential energy per unit charge, sometimes called voltage. So here it is. Electric potential is electric potential energy divided by the amount of charge. So for example, and it also has a unit. 1 volt is 1 joule of electric potential energy per Coulomb of electric charge. So if you have some big object that's positively charged and you have two objects that are the same distance away from it, you say these two objects have the same electric potential in volts, but since this object is smaller, has a smaller charge, it has a smaller electric potential energy than this bigger object. Lastly, I want to talk about capacitors. You can store electric potential energy using two parallel conducting plates that are separated by some distance. If you hook them to a battery, the battery can pull negative charge off one plate and push it onto another plate. So the minus is connected to the negative plate, the plus is connected to the plus plate. And there's an attractive force here, so that if you now take this capacitor and hook it to something else like a motor, then as it discharges, it can release its electric potential energy and drive a motor.